Okay, so here we are in the implicit function theorem, and we have defined our open sets u and w and our function x, and we would like to prove that 1, 2, and 3 hold. So let's get started with 1. That's what this video will be about. Okay, so here we are. We've defined x like this. So our goal is to show, so here's a picture from earlier, we've kind of defined x to be the first component, pi superscript 1, of what I get when I apply the inverse of this function to 0, comma y. So I want to show that this does what I think, that it gives me, for any given y, the unique x that pairs with it. Whereby pairs with it, I mean has the property that f of xy equals 0, so satisfies that list of equations that little f is specifying. Okay. So now I claim that if I take 0y and I apply f restricted to u inverse to that, I claim that that gives me what I've called x of y, comma y. So this claim will help me in what I'm doing next. So the reason I'm making this claim is that this is kind of summarizing what's in this picture. This picture, by the way, is not part of the proof. It's just like a random picture. So this is part of scratch work, but I'm going to keep it up because I keep pointing to it. So not in proof. Because it's not making an argument, right? What would this do in the proof? It's just a picture. Okay, so what I want to prove now is that what is being suggested by this picture is actually correct. That when I take 0, comma y and apply the inverse of this function to it, that I really do get the thing that I defined, x, capital X of y down here, and then along with that I should get y also. So that's my claim here. For all y and w is what I meant to say here. So proof of claim. Let's fix y and w. Then, okay, so let me start with the left-hand side here. And let me apply f to it. Okay, so if I apply f to it, I should get 0y, right? F of f inverse of 0y. And on the other hand, going back up here to the definition of capital F, the way it operates is you put in xy, and then it takes f of the entire thing that you put in, comma, and then it gives you just the second component. So you can think of it like this, as giving you f of the entire thing that you put in, and then for the second component it gives you the second component of the thing you put in, which I'm calling pi 2 of the thing you put in. So pi 2 of xy. So that's a way of thinking about how capital F works. So then here, when I apply capital F to this thing, I get little f of this thing for my first component, the little f of the whole thing that I put in, and for the second component, I get the second component of what I put in, which is y. Sorry, that was an error. The second component of what I put into capital F, which is the second component of this. So pi 2 of this. There. So overall, I've got zero is this first part, and y is that second part. Now, this portion here, this n plus m tuple, is made out of its first part and its second part. So I can break it down. So let me break it down like this. I can break this thing down into its first part and its second part. So that's pi 1 of it, f restricted to u inverse 0y, comma pi 2 of it. And pi 1 of it, that's what I have defined to be x of y. That's how I defined capital X. So let me go ahead and write that down. X of y. And here I have pi 2 of this. Just counting parentheses. I think it's good. Yeah, okay, so what I have here, the second component of this thing, inverse of y, that's y. So this is notationally looking complicated, but it's this idea that we had in the picture. It's just that if going forwards you just keep the second component as y, then going backwards you're going to keep it as y also. So this is what's being captured by what you see here. Y is pi 2 of this thing. This here is y. So this is y. So 0 is f of xy, comma y. Okay, great. And that's telling me what I think about the way I defined x of y. X of y is supposed to be the x that goes with y, in the sense that this happens, in the sense that together with y, the list of equations specified by little f is satisfied. So that's good, and actually I think that's all I really wanted out of this claim, so I'm not sure why I phrased it so strangely here. I think I was just trying to write down something that looks close to what this picture in my head was depicting. But really all I wanted for the claim is this, I think. 0 equals that. Okay, so great, that's proven. Now, where do we stand in terms of the implicit function theorem proof? Here was the statement, and we were working on proving 1, 2, and 3, and we have proven, well, we've proven this second bullet point about number 1. How about the first bullet point? Y is x of y, comma y in u. So if y is in w, this was our definition of w, if y is in w, then 0, comma y is in v, right? So then if we take 0, comma y and we apply the inverse of this function, that's something in v, and we're applying the inverse of this function, then we end up with something in u. So that's going to be the reason for having x of y, comma y be in u when y is in w. Okay, so I just came down here to back to our claim that we were working on, and I added this sentence. Also, x of y comma y is in U. I would like to add that to what the claim is claiming. So for all y and w. So I would like a more solid justification for that here, and here it is. So look at what we have overall here. 0 comma y equals this pair, where the second portion is this thing that I keep underlining in yellow, which we have shown to be y, right? And the first part, so 0 comma y, is okay, sorry, I keep messing this up, so don't focus on that, no. X of y comma y is in U because, so I'm just trying to formally write down what argument I was making earlier using the picture. X of y comma y is, and then look at the way x of y is defined. X of y is, where did I define it? X of y is the first component, pi 1, of this thing. So like that, x of y is pi 1 of this thing. That was the definition. And then y, we have seen that another way to write y is as pi 2 of that very same thing. So that's what we're seeing here, is pi 2 of the same thing. Just like that. And yeah, if you take a pair where the first portion is pi 1 of something and the second portion is pi 2 of that thing, then you're just taking that thing, right? This is just the entire thing. So you can see x of y comma y is this function applied to 0 comma y, and 0 comma y is in V. Why? Because y is in W, and that's the definition of W. The definition of W is that it contains those y's with the property that 0 comma y is in V. So that sort of shows you, I think this claim has captured everything that seemed intuitively correct from looking at this picture. All right, so that's the beginning and end of the claim. So let's section this off. The claim is done here. Okay, so that's 2 bullet points established of the 3 bullet points above. So the claim has established in our proof of the implicit function theorem of part 1, conclusion number 1, it's established these 2 bullet points. And it remains to look at uniqueness for conclusion number 1 here. X of y is unique with respect to having this property that it's an x that gets paired with y. So let's work on that. So for uniqueness, suppose you have some other little x. So to prove uniqueness, first fix a y in W, and assume that you have some other x, let's call it little x, and it satisfies those first 2 bullet points. So little x comma little y is in U, and second bullet point, f of little x little y is 0. Then my goal is to prove that little x is none other than big X of y. So then focus on capital F of little x little y. So by definition, that's little f of little x little y, comma y. That's how capital F works. And we're assuming the second bullet point here, that's 0, comma y. And this is another way of writing, as we have just seen in the claim here. This fact about capital X of y is f of capital X of y comma y is another way of writing 0. So this is also no. I'm trying to, well, my goal is to use the injectivity of capital F. So what I actually want to use, let me see here. I want to use something else inside the claim. So again, I did not make the claim flexible enough. Where is it? This. Yeah, this should really be part of the claim. This statement that if I apply capital F to both sides here, capital F of this thing is 0, comma y. So that's let me add that to the claim here. And capital F of x of y is, I guess that's actually immediate from the definition of capital F. Never mind, the claim is fine. Okay. Right, yeah, I was on the right track. Sorry about that. I'm fine here. So 0 is another way of writing x of y, f of x of y, right? So this here is 0, according to what is already in the claim. And then this is, by definition, of capital F of x of y, comma y. Okay, now, since xy and capital X, y are both in U, this being in U, that was also part of the claim above, and f restricted to U is a bijection, so specifically is injective here. We have little x is none other than the original capital X of y. Okay, so this proves conclusion number 1 in our implicit function theorem statement here. So we've proven conclusion number 1. For any given y and w, there's a unique x that goes with it, and that x is the one we specified when we defined the function capital X in our proof. So it's capital X of y. Okay, so in the next videos we'll finish up the proof and prove parts 2 and 3 here.